We're going to jump into flat dynamics here. And so this is how we connect the topics we talked about, dynamics and kinematics. So Newton's second law shows the relationship between kinematics and dynamics. And if you remember, that is net force equals mass times acceleration. So in other words, this A right here is the bridge, because we had that in all of our kinematics equations. Now we have it in our forces. And you've actually seen this in the previous video. You would have looked at how I calculated the acceleration of a box that was sliding, and then I used that to find a force. So let's look at a couple more examples here. We've got a 35 kilogram dolphin decelerates from 12 to 7.5 meters per second in 2.3 seconds to join another dolphin in play. What is the average force that was exerted to slow him if he was moving horizontally? The gravitational force is balanced by the buoyant force of the water. So we've got mass equals 35 kilograms. We've got an initial speed of 12 meters per second. We've got a final speed of 7.5 meters per second, a delta t of 2.3 seconds, and then if I draw my free body diagram, the buoyant force will equal to the gravitational force, and then we'll have the force, we'll call it the slowing force, the water resistance, if you will. So the net force, when we add this up, the net force, and let's just look at the x direction, is going to equal ma. So the net force in the x direction equals m times a. We don't know a yet, but we can find it from our expression up here. So v minus v naught over delta t will equal our a. So net force equals ma equals fs, because there's only one force in the x direction. And if you remember, as long as we're dealing with everything in the same direction, be it x or y, we can ignore what's happening in the other dimensions. We're looking for the average force. So the average force should equal the mass times the acceleration. So that should be m times v minus v naught over delta t, which will equal 35 kilograms times 7.5 minus meters per second minus 12 meters per second over 2.3 seconds. 7.5 minus 12 is going to give us 4.5 divided by 2.3. 2.3 times 2 would be 4.6, so this is right around 2. So our net force for slowing down should be around 70 newtons. You can go in and calculate that yourself to see how close, but you should be in the ballpark of 70, give or take. Okay, for our second example, a 2.5 kilogram fireworks shell is fired straight up from a mortar and reaches a height of 110 meters. The mortar tube itself is a tube 4.5 meters, 0.45 meters long. What's the average force on the shell in the mortar? So I will say that this is a bit of a challenge compared to what you might expect on the mastery check, but it is something that should be totally achievable kind of on your own eventually. So let's start. If we fire straight up from a mortar and reach a height of 110 meters, delta y equals 110. The initial velocity in the y direction is unknown. The final velocity, though, at the maximum height, we know is 0 meters per second. The entire time that it's in the air, a equals negative g equals negative 9.8 meters per second squared, because it's pointed down. And we can use all this to find this initial velocity. Why does that help us? Because in this part right here, we have, we'll call it v negative 1 before the launch is equal to 0 meters per second. And so what's this a1? We don't know, but if we figured that out, we can find out the acceleration. To find the acceleration, we can find the force. So let's first find the initial velocity when it leaves the tube, or the velocity when it leaves the tube. So if we've got velocities, positions, and accelerations, that means we're going to do v squared equals v naught squared plus 2a delta y in this case. So v squared is 0 equals v initial squared plus 2a delta y, and I'll just write g there. V naught equals the square root of negative 2g delta y. Then we need to find this other acceleration. So we've got the same setup of v's, accelerations, and y's. The difference here is now we want to find v negative 1. So v final, which is going to actually be labeled as v0 because we're going from negative 1 to 0, equals v negative 1 squared plus 2 unknown a, so that's a1, times delta y1. And that means v negative 1 squared is 0. So we have negative 2g delta y is equal to 2a1 delta y1. The 2's can cancel, and we'll get negative g delta y over delta y1 equals a1. Delta y, remember, is 110. So we're going to get 9.8 meters per second squared times 110 meters divided by 0.45 meters. And that will give us A1. And then we just need to find the net force equals the mass times the acceleration. And they're asking for average force. So that's just what force would be required to give us an A1. So net force is equal to the mass, which is, well, this would be A1. So M times negative g delta y over delta y1. Net force is equal to 2.5 kilograms times negative 9.8 meters per second squared times 110 meters divided by 0.45 meters. 0.45 is just less than half. 9.8 is just less than 9. So if we double this, I'm going to say that doubles to about 20. Sorry, that should be a positive because the g was a negative. So 20 times 110 is 220 times 2.5 is going to be approximately 220 times 2.5 would be approximately 330 newtons. That's not going to be the best approximation, but it'll be close. So that's our answer in newtons. And then as a ratio to the weight of the shell, well, we're just going to need to divide by the weight, which is 2.5. It's going to equal the force divided by 2.5 kilograms times 9.8 meters per second squared. which if we look back, the force as the ratio of the weight will equal 110 meters over 0.45 meters times Fg. Because we're dividing out the 2.5 and the 9.8. So that's where we get this ratio if you look up above. Again, this is more challenging than you necessarily expected to do right off the bat, but it's a good example of how we can combine all this together.